Hi, I'm Roger Palmer with PASCO Scientific, and today we're going to learn a little bit about the resources all around us. And one of those resources is that which gives us all life, and that I'm going to talk about is the soil. Soil is a wonderful resource that's a combination of both inorganic, non-living things like the rocks that first came from the crust of the earth, plus the components of the living materials that are down in there, the roots of plants and the bugs that live in that. The air itself can get down in there and gases are exchanged, and of course water is all necessary, but that's all needed for us to be supported in terms of the growing things that we depend on and enjoy like you see around us. So we're going to go down and talk about the collection of soils. First of all, if you look around, you'll see that we're in a grassy soil, lots of carbon that grows every year, and then some of it dies and leaves some litter there. If we get down to this level, I think you'll notice that we've got things like leaves. We've got the grass itself that's died. If you get down into the bottom, it's got a wonderful set of roots. All of this is wonderful material for what then lives inside of that soil. The bugs, the insects, the decomposers that make it rich. When they eat that material, the manure they leave behind is going to be wonderful for the next generation of plants and materials that continue to grow here. We're going to just take any kind of a device that you can dig with, a trowel, or if you got a little shovel. We're going to loosen it up first. Get down into this. You can see it's kind of a grayish black, nice, lots of organic material. We're going to take 3 other samples besides this one, which are already back in the lab, and we'll compare those. All right, so I've got a nice set of material. We're going to add that to our bag. Try to get as much of it as we can just to be the soil, okay? If it's surface materials, I'll take that out. Maybe one more, but we want a good, probably 1 to 2 cups of material that we're going to use to test when we get back inside. I'll go ahead and break that up a little bit so that we'll be ready for it when we get inside, when we want to mix it to see its both chemical and physical properties back in the lab. Thanks. All right, now that we've brought our samples back into the lab, I want to talk just quickly about the tests that we would want to do, and we'll talk about how to do them separate. But just in the background, what makes soil have good quality? Now, one of the things we talked about is that soil is made up of a complex mixture of things. It's made up of the rocks, the bedrock that's there and broken into small pieces. It's made up of organic material, living things that are in there. It's made up of both the gases that are inside and the liquid, the water that carries a lot of these nutrients. Now, what we want to do is test for those. One of the things that we can do to test in terms of the physical material, we can take a look even just with a small magnifying glass that you might have and look at the grains, take a look at the materials you might see that are in there that came from materials that are still in process of becoming good soil, like the past generations of grasses, leaves, even old insects or whatever that you can see in there. And see if you can't tell and see if that's that organic portion. You can tell the crystal sizes, how much sand is in there. If there's little particles, it's silt and it's really fine. But that'll help you to determine that. The next piece that we're going to determine is the biological activity. Everything that's living is going to be breathing and consuming materials in there, just like we do in respiration. So we're going to put the CO2 sensor onto each of those soils that we tested to see if we can't determine sort of how active that soil is. The next, we can tell what's dissolved in the soils when we add some water to those with the conductivity sensor. It's a general measure, and it shouldn't measure anything that's ionic that dissolves. So we're going to have the chance to see the salts, the ionic compounds that are in there and that are dissolving. Finally, we'll finish off by taking a look at the pH of the materials and determine sort of the quality of the life in there that's involved. Some of the minerals may change the pH. Some of the plant materials can change the pH. And so, if you're in pine forests or some of the leaf materials that can fall in there have tannins, which are going to be more acidic, and the soils might have something more like, limestone, which is going to be a little more basic. So we'll determine that here in the experimental measurement portion. Now that we've got the samples back in the lab, we want to make sure that our instruments are ready and are set so that they're going to give you the best measurements. Each of these has got a calibration procedure, and I'm going to show you the CO2 process. You can always look these up in the manuals that come with the kits, or you can look on PASCO.com on the product pages, because in the documents sections the manuals are listed, and many of these have films as well that you can watch to see how the calibration should work. So this CO2 sensor is already connected to the interface. What I'm going to do is just go down to the bottom here and hit the calibrate. When we do this, we're going to measure the CO2 that's in a fixed body. So that should capture about 400 parts per million. I'm going to leave that right here. Maybe, there we go. And then I'm going to just go down and calibrate. It's a 1-point calibration for this one, and that should be set. Okay, so that's calibrating your CO2 sensor. Next, we're going to take a look at the conductivity of the soil using the soil wireless conductivity sensor. I'm going to switch over to seeing those values on that page. But in terms of setting this up, all we're doing is going ahead and taking the guard off, turning this on. We're going to need to take about a penny's worth of soil in each of these samples. I'll show you what that looks like. And small sample of your soil. Here's our grassy soils. Okay, we're going to put those in the bottom of a beaker. Here we have our soil from the trees underneath a set of pine trees. And this is soil that's in a potting bed. And then this is soil down by the creek. It's a lot more sandy, you can see. So now we each have the soil amounts in there. What we're going to do is add 40 mils of water to each of these so that you can take your conductivity sensor. I'll just use one of these, this one that I just finished. And I have a mark at the bottom at 50, and so I'll mark it to just below that. Okay, a little bit more. There we go. You want to get those nice and soluble. So that's going to be dissolving any of the salts that are ionic substances that are in each of those. Then the next ones that are going to come up, once you've measured the conductivity of each of these, you're going to use the pH sensor as this settles, and you're going to try not to touch the soils with the bottom. You're going to take the cap off. Usually I take this cap. And if I'm out in the field, I don't like to take this off. I usually push it up just to hold onto it here. But we're inside the lab, so I'll go ahead and remove that. You'll go ahead and turn that sensor on, and you're going to be able to go in. And again, if you can not touch the actual soil itself, the glass probe is right there. So maybe if you're off to the side, and you can slowly move those. Make sure that this is sitting for a couple of minutes while it's dissolving, and then you can be able to measure each of these. When that's finished, what we're going to do to finish testing is going to use 40 mils of acid to see how much the soils have a capacity to resist pH change. So in that case, you're going to measure out 40 mils. I start off here at 100. I'm going to make sure I measure down to about 60, just a little bit more. So that should be about equal volume as what you started off with in terms of your water. And we're going to pour those into each of these substances to measure the pH change with that pH sensor. So first time through, you're measuring just the pH of the solution to see if there's substances dissolved in the soil that are going to change the pH from neutral, 7, and then next you're going to add the acid and remeasure each of those again. Between each, you're going to use the distilled water to rinse the bottom off, and we'll show you that in the collection phase. We've got our samples out, and in terms of putting each sample into the bottle, before we start to measure those, we do want to make physical observations. And so if I lay these down, I can take a magnifying glass, and this is really a good level. I can take a look in there. I don't see any bugs. This is the grasslands soil that was there. Usually those are richer and darker than let's say river bottom soils or something along those lines. It does have a grayish look to it. Lots of roots that I'm looking in there. I'm looking closely. I don't see any sand. Really, it's clumps that if I break down, it's very fine parts that if the wind was blowing, it would be almost like dust. Now, the next one that we're going to go to on here, and I'll label each of these before we finish so we don't forget which is which, This one came from underneath some of the pine trees that are here, and so it had a leafy sort of litter, the light pine needle litter. It's much finer soil, I would say, as I'm taking a look at those. I do see a little bit of sand in there, or grit, that I don't see in the grasslands. The trees don't have any grass under them, so if there's wind that's blowing by, it would be probably easier to be caught in there than in the grasslands. I see a few needles. Let's see. Don't see any evidence of anything crawling in there, any kind of bugs or anything like that. But as you see in the CO2, when we measure that, we'll see if there's something that's decomposers or something that's going on. Now, this one was in the potting soil where the flowers were. And so it's a much finer mesh, but it's also stickier. Now the water was on, I suppose, in the last 2 days, so that it's got some water. You can see that there's some evaporation going in. It's got some green grass growing, like moss growing in there. As I'm taking a look, I can see a little movement, so there may be a few bugs in there, and but it's also fine. But it's got a different feel. It's a little smoother when it rubs between my fingers when we collected it. So those are just some things about this one. Was the potting soil, and the last one was down by the river. And if I take a look here, I can easily see larger sections of sand, gravel, and they have different colors like quartz, which is white. It's got a little bit of pinkish to it, so that's probably the feldspar crystals. But I can see all sorts of different size little rocks that are inside of that stream, which is great. It rinses quickly so that the water can pass through there. So in each of these, I'm going to just jot a note right here on the beakers themselves. So this one, in terms of where our starting was underneath the grass or the prairie. That's sample 1. Sample 2 was underneath the pine trees. So I'll put under pine or under woods, forest. That's sample 2. Didn't have much for grass, just open dirt. A few little things were growing. In the garden area, the garden soil, it did have a fine sort of a moss that was growing in there. So this was the garden. And I believe at one point we started off probably with peat moss or something from a store to start those plants growing. Last one came from the creek, so it was a sandy creek right on the shores. And so that is sample 4. Let me make sure I put 3 on this one. Okay, so those are all labeled as we go through and as you see the data. Each of those has come in. I've made some just verbal sort of observations. If you're keeping notes, it's important always to look for those kinds of things. The first thing we said we were going to do is to hook up the CO2 to each one of these. I'm going to show you this process for one. If you are opening the CO2 sensor data on the SparkView, you're going to see that you'll have all 4 of these. If you're going to run it yourself, that's fine. That you're going to hook up each one of these and run them separately. Each is a different run. And here's the soil that we used in the grasslands. I've got the other 3 that will be here for you if you are doing this from home, for instance, that you will have. If you open up the lab that goes along with this, you're going to have all of these 4 readings. I'm going to just demonstrate this process. So first of all, you want to make sure that the soil has gotten broken down into small enough particles so you can either take it in the bag if you're doing this yourself and break those clumps up. That's a good method to do these. If you've got a pestle, you could do that in a pestle as well. So it'd be nice and fine. But I think, small particles are going to be just fine. Next, we're going to put into here about 40 mils. The bottom mark here is about 50, and you can see I've done that. And then we're going to take our CO2 sensor. We're going to put that in here. Okay, we're going to follow the CO2 sensor, the CO2 amount. I'm going to get it nice and flat across the bottom so that any CO2 that's generated will have maximum surface area for the CO2 to escape and be measured. And then we're going to come down to the bottom and we're going to run this for 10 minutes. So I'll go ahead and start this and we'll let the film progress a little faster for these 10 minutes while you see the data come off. All right, I'm coming up to 600. Next. what we're going to see is I'm going to now take and use the conductivity sensor. We've got each of our samples here. I did go back and I added a little bit more because it said 40 mils, not 40 grams of the soil. So I went back and measured to make sure I had about the first mark of each of these, which is marked at 40. So we had equal parts of soil, water, and that's going to come in when we add the vinegar too to see the buffering capacity. But the best you can do is hope to get these to settle as much as possible as opposed to letting these sit down into the soil. You're going to want to put these in the water column, so just sort of at the surface. As a matter of fact, what we can do is, if you have a bigger beaker, is I can get the sediments to go one side and then I can put the sensor on the other side. Let's make sure we're still connected. Look on my live meter. That's moving on the conductivity, so that's good. I'm going to go ahead and in the new wireless probes that you can test the same sample with two different probes. In the past, it used to create a circuit if you had multiple probes in the same sensor. So the wireless are good to work in that sense. I'm going to go ahead and sort of get the particles out of the way and put that right here. What's nice is on the first page of SparkView, you're going to see that it's got a dashboard to be able to sense this. All right, so we'll go ahead and we'll click on that. And on the second page, you're going to see that's the current CO2 sensor, but we've got a time graph that's going on and being collected that you're going to use for comparison. I'm going to let those settle for just a little bit, make sure the values look pretty good. They get to be stable. There we go. They both look pretty good. Okay, and from there you would then work that solution one, and I'll measure the others for you if you're doing this from home, and they'll be in sample run 2, sample run 3, and sample run 4. Now, the last thing we're going to do is to determine the soil's capacity to resist an acid change. So here's where I poured 40 mils of my vinegar into a separate beaker here, and I was going to then introduce that to this first soil sample, which came from the grasslands. I'm going to go ahead, we're going to put that in, and I'm going to go ahead and pour in the vinegar. What I think I'll do is just give that a little bit of a stir, just to make sure that mixes thoroughly. Okay, we still have some of the roots and the organic material that sort of float to the top. I can look to see if there's any evidence of bubbles, to see if there's something like carbonates from a soil, if you've got limestone soil. But I'm going to go ahead and put that back in, and we're going to run to the third page and make sure that's going. And let's watch to see when you first put the acid in, and I'll zoom to the results here. When you first put the acid in, it's a solid that the solids of the soil is what it's reacting with. So we're going to see if that has any chance to change or if it just stays. You'll notice the pH values are around 2.7, which is in the smaller than 7 or the acid range. And we're going to give it a minute or so just to see how that range, if it's slowly changing, if there's a trend in there. You can see the values are very small and close together, 2.6, 2.64, 2.66. So any big changes are really quite small. If I would zoom out a little bit, we're going to let it run for a minute here and determine what kind of a change. Actually, it says 5 minutes to make sure that if there's a solid in there, that it can react to it. And that's called the buffering capacity of the soils. We can see the pH has gone ever so slightly up or higher. It's got a little bit of resistance to change, but we'll see when we're all said and done in the analysis section. We'll talk about that. And the time isn't over yet, so this may go back down. That may be in the range of the variation of the sensor itself. As this is running, one of the things that you'll want to make sure, as you're testing this yourself, I took and mixed these a little earlier, but if you let them sit for 5 to 10 minutes, you're going to notice that the solids particles are going to sit and sift down to the bottom, and it'll be easier to get a reading of what the water is that's been in contact with the soil. And that's what these probes are measuring, what's happening inside of the water quality of the soil. Sorry, the water in contact with the soil. Let it go for another 20 seconds. And we'll get 3 minutes worth of testing to see the buffering capacity of this soil. Okay, so if you're at home, we'll have the runs for each of these soil types that you can open up. If you're running this in your own lab with your own soil types, then go ahead and get started so that you'll be able to analyze sort of the qualities of the soil that you've collected. We've gathered all the data about the materials, the processes, and the properties of the soils that we've seen. Using carbon dioxide to determine what kind of life processes are going on and the respiration that's happening for those decomposers and small bugs and things that are in the soil. We've used the conductivity sensor to determine what minerals are dissolvable, ionic compounds and things that can dissolve in the water are going to show up in those. And then we looked at the pH as well of the soils that we mixed with water. So as we went through that analysis, we really started with just even an inspection. And as we looked at those, this area is really a grasslands. And so most of the soils you can see are fairly dark. That had been there. If looking at the prairie grasses itself, it had clumps. And so those are probably the clay particles, those small clay particles. If you crush them with your finger, they become extremely fine. And so more clay than loam or more clay than sand. And so if you're using a soil triangle, you could place that more into the sort of side of the clay, but you could look at those. The thing that's different is the garden soil is a much darker soil. It's got a lot more organic material and probably was used some sort of peat or something which is typical, like potting soil, which has a lot more decomposed like grasses and mosses from the peat sources that they come from. And then the last one that's a little different as well is the sandy texture of the creek soil that's being transported, and the source of that's even just outside the region. But that sand should help you to determine in the soil triangle which of these types of soils we're talking about. You can look up on those just from your observations. The next is when we went into take a look at the carbon dioxide or the sort of living biota, the examples of what's going on. If we take a look at our page where we did our four soil quality samples with the CO2 sensor, you're going to notice one was way up there, and that was this garden soil, which was a little more moist and it had a lot more. It had like fungus and some algae and things that were growing in there. So not sure, but the jar itself is a little more moist, and so that's going to encourage decomposing as well than these drier soils that were there, except for the river sample, the soil near the creek. And so we had one that was quite a bit higher. Now, that's still not, while the bottle could have filled while we were doing our testing and those kinds of things, probably a better determiner of how much biological activity is in there is going to be by the rate or the slope of any one of those lines. And so let's take a look at how to do that. I'm going to turn those other graphs off for right now, and we'll just look at one of the samples. And then, of course, you can look at your own, or you can look at the data that we're providing for you. And so let's zoom into that graph. And to determine this region slope, to determine how fast per time that CO2 is being developed, we're going to make sort of a box that goes around there. So we highlight the tools down here. You expand this set of tools down in the bottom corner, grab the box and select region. We're going to choose a big section of this so we get a good average of what the rate of carbon dioxide generation is. So I'll highlight that area. You'll notice that if I'm in the box itself, you're going to see that you have some tools within it. That would be one way to put the best line through that data. If you're not seeing that, you could also come down to the bottom where show the best linear fit. I'll go ahead and click that, and they're going to come up with some statistics about the best line that fits through there. The line that you're going to take a look for and compare to the others is the slope. The slope portion is the M, or 0.146. Each of those is using the units that are in here, parts per million per second. And so that's going to be your comparable number to the others to see which of these soils is biologically most active. Okay. Now, let's go on from CO2, and we can take a look at our conductivity to see which one's got more minerals that are dissolved. As we take a look at that, I've got it right now set to our sample 1, which again is the grassland sample. The grassland sample, when dissolved in water, had a 453 microsiemens per centimeter, and that's just the distance between the ends of these probes. So it's determining how much electricity can flow through there. Typically, soils can take up to about a 700 before then the plants, if there's that much saltiness, it's hard for the plants to draw the water and the nutrients up into it. So it's quite a bit below those. If you looked at the grasslands that are there, there was a broad variety of native grasses, lots of seeds, natural wheats and barleys and side oats and things like that. That if I was, just walking in there, it's a nature trail, a city's sort of supported center. And so it looks like it's very fertile and things are growing. So it's well below the 700 sort of microsiemens that would start to make specialty plants that can grow in only saline sort of soils. The next piece is we're going to take a look at is we have our pH sensor. The pH sensor is going to measure and determine whether there's, if it's more basic, higher than 7, it's going to have some more limestone kinds of components to it. Plants, especially in the middle of the United States where the old shallow ocean used to be, as the continents were forming, had deposited a lot more limestone in those kinds of times, and they would see that their pHs would go higher than 7 because it has the limestone as a basic, lightly basic component. If it's more sandy, rocky kind of soils, especially in higher altitudes where more gases can dissolve, if it's cooler, you might run into where it's a little more acidic, where not much is dissolving from the solid parts, and so the gases in the air themselves will control the pH that's available. If they have leaves, leaves themselves have tannins, which are going to be just a touch more acidic, and maybe some leaves that fall down from trees and those kinds of areas that help to make the soils. So they may be there, but really 7.2 is a very natural, normal amount to expect for living things to be there. It's right around 7, which is in the middle of the scale, which is where things are most happy. All right, so last we're going to take a look at is the pH of our soils. Now we've got all of them turned on, so let's just take again a look at our first sample, sample 1. I'll go and turn these guys off so that we just take a look at the second run, which is the buffering run for us. And we want to take a look to see, did this change over time? Soils that have carbonates like limestones, or that they used to be places where reefs may have formed in shallow oceans in the past, even if they've been lifted up or changed, would have this capability to take out acids, and they're resistant to acid rains. If I look at this, it looks like there's a slight trend that may be going up. It's hard to tell. But if I look closer at this left side, notice I'm really right at 2.8. This is very small change, less than 1/10 of a pH. And so I don't see much change at all. And you can take a look at the other soils in this region. Our area of central California, where these soil samples were taken, I wouldn't have much expectation to see a lot of limestone or buffering capability to protect from sources of acid rain. Now, if you're taking your own samples, that's what you would look for to see if there's a slight trend where this is starting to recover and it's neutralizing acids. We're down here in the 2.8 where the vinegar is naturally, and we don't see much of a change over those 3 minutes that we let the sample sit there. So altogether, from the texture and the visible sort of look at the soil, we can analyze where in the soil triangle that sample of soil is. We took a look at the biological activity with the carbon dioxide and determined whether which of these is still your job to do the analysis to see which of these is more biologically active, whether that's decomposers or small bugs that are doing the decomposition and active in that soil. We've got the conductivity, which is going to tell us a little bit about what kinds of minerals dissolve that are in that area. And the last one is the healthiness for plants and things that live there, for young especially, young bug eggs or something like that will be affected by pH. So the farther we get away from neutral water, 7, the less likely that can really foster a rich biological community inside your soil. So when you're done, come to a conclusion based on what you see and what you've measured, or if you want to use our samples, all 4 of these soils, again, from grasslands. We took some sample of soil underneath the forest, pine forest, so it had a bunch of pine needles there. This is the garden soil that was probably used, and soil came in like peat that was enriched. And the last one was the sandier soil from the creek bottom. So as you're doing your analysis, before you turn that in, make sure you make some statements about which of the combined, all of those 4 factors we took a look at, create a soil that's got the highest quality. Good luck with your report, and look forward to having a teacher take a look at your work.